And again, we are reasoning about risk. So this talk builds on the previous one. Our presenter is Ashkan Jasser, and the talk is about risk-bounded nonlinear planning. So you can see that this is kind of part two with respect to what we have seen in the previous one.
Yeah. Thank you, Sarah. Okay, let's get started. So this talk is about planning under probabilistic uncertainties, and we want to see how we can consider these uncertainties when we are doing planning for robots and in general for autonomous systems. So in general, we have a set of powerful techniques for motion planning and control of robots and in general for autonomous systems. A set of techniques that can make robots run, walk, fly, and even swim, like working robots of Boston Dynamics, or reusable launch system of SpaceX, or autonomous vehicles. But behind the scene of these cool videos, we have uncertainty that is trying hard to ruin our designed plans. So in practice, we have different sources of uncertainties. For example, uncertainties that come from environment, like uncertain rough terrain for walking robots, or wind disturbances for flying robots. Or we have sensing uncertainties when we are localizing obstacles and robots in the environment, or even uncertain parameters of the models of the robot itself. So simply what we are doing, so we are designing a trajectory to drive a robot from given initial point to the goal state, and due to uncertainties, robot deviates from this planned trajectory and ends up in an unstable pose and simply fails. For example, unstable pose for an Atlas robot, or unstable pose for a SpaceX launch system. Even if we have a perfect information about environment, even if we have a perfect sensors and precise models for robots, the intention of other players are uncertain to us. For example, when we are planning for autonomous vehicles, the intention of other vehicles are uncertain. Their future behavior, their future actions are uncertain to us. So we need to deal with this kind of uncertainties when we are planning for robots and autonomous systems. In general, we have two sets of techniques to deal with uncertainties. First, robust approaches, and next, risk-bounded, or in general, risk-aware techniques. In robust approaches, we need to look at the uncertainty set. We need to look at the range of uncertainty and make sure that obtained plan is valid for all possible values of the uncertainties. Let's see how it works. For example, consider this simple example. In here, the goal is to drive the robot to the goal region, and we have TurtleBot that plays the role of obstacle. In this problem, we don't have any uncertainties, so we can call any path planning algorithms like RRT star, or PRM, or trajectory optimization techniques to construct a path to the goal. Now, let's look at next scenario. In this scenario, TurtleBot plays the role of moving obstacle, and its location is uncertain. We only know that the robot moves between these two given points in the room. Now, to construct the robust path, we need to look at the uncertainty set, which here is the interval that shows the location of the robot. And we have to construct a path such that for all possible values of the uncertain parameters, which is here the location of robot, the path is obstacle-free and safe. So it means that we have to use this free space and construct the path to the goal. Now, no matter how this obstacle moves, no matter how this uncertainty plays, we are always safe. So this is robust planning. Now, what is wrong with this kind of reasoning? Looking for a plan that is valid for all possible values of uncertainty.
It doesn't always exist. Or may not always exist.
Right, that's true. So to see this, consider the next scenario. Here we have a larger uncertainty set. the obstacles moves from that side to this side of the room. So no matter how we construct the path, we always find a value for uncertain parameters, or we can find a location for our obstacles that collides with our path. So from robust techniques point of view, this problem is infeasible. And even worse, if we replace this turtle butt with a real turtle that takes 10 days to get to this part of the room, still from robust techniques point of view, this problem is infeasible. Because we can always find a location for our uncertain obstacles that collides with the constructed path. So in general, robust techniques results in conservative plans and conservative solution. Now the question is how we can avoid these conservative plans. How should we fix our reasoning?
Include
Timing? Maybe.
I mean, if you know if you can predict.
So we don't have any information about our uncertainties. So if we have a model or time-based model, we can do an exact prediction. But here, we only given some uncertain set. So to avoid this conservative solution, we are going to use risk-bounded techniques. So based on risk-bounded techniques, instead of looking at the uncertainty set itself, we are going to look at the frequency of the uncertainty. How frequent is to observe these obstacles in this part of the room? And frequency of the uncertainty is nothing but probability distribution of uncertainty. So if you look at the probability distribution of the location of our obstacle, we may see that there is a small probability of observing the obstacle in this part of the room. So we can use that space to construct our path to the goal. But since there is still a small probability of observing obstacle in that part of the room, there is a small probability of collision, and as a result, there is a small probability of failure of the obtained plan. In the risk-bounded techniques, we are looking for plans to make sure that probability of failure is always bounded by predefined value delta. We call this delta as an admissible risk bound. Or equivalently, we are looking for plans that probability of success is greater than predefined value 1 minus delta. This is how we want to guarantee success in stochastic frameworks. So this is the plan, and this plan, for example, is going to work for 90% of the time. So probabilistic reasoning and probabilistic guarantees. In general, robust techniques versus risk-bounded techniques about possibility versus probability. In robust techniques, we either can fail or succeed. 0 and 1, we have 2 outcomes. But on the other hand, in risk-bounded techniques, not only we can succeed or fail, but also we can design the degree of this failure or success. So we receive 0, 1, and whatever is in between. So mathematically speaking, we have more freedom, we have more option to design the plans. And this will result in a less conservative plans for our robots. Okay, so let's now look at mathematical formulation of the risk-bounded techniques and some challenge that we are going to face. So in risk-bounded motion planning, we are usually given a model of robots. So we are usually have a continuous state space model. In this model, so the vector x describes the states of the robot. For example, these states could be location, velocity of a vehicle, or it could be joint angles and angular velocity of a walking robot or a manipulator. So given this model, and given the current states and the current current control inputs of the robot, we can predict the next step, the states of the system at the next sampling time. We are modeling uncertainty with the uncertain parameter omega. Omega has some probability distribution that captures all distributions of the system. Also, we are given description of safe set or unsafe set in the state space. For example, description of the obstacles or description of the safe regions in the environment. Now, given this definition, we define risk at time k as a probability of failure, probability that the states of the system at time k collides with obstacles, or equivalently, probability that the states of the system at time k doesn't belong to the safe region. Now, given these descriptions and model of the robot, in the risk-bounded planning, we are looking for control inputs over a planning horizon t such that we drive the robot from the given location to the goal region in the state space with respect to probabilistic safety constraints. At each time k, probability of collision, probability of failure should be bounded by predefined value delta k, or equivalently probability of success at each time k should be greater than predefined value 1 minus delta k. In this talk, I assume that we are given this risk bound. So this morning, Ono talked about risk allocation techniques to come up with this admissible risk bound. We can apply these techniques and come up with, at each time k, we can decide this risk bound. But in this talk, I assume that these delta k's are given. Now, let's look at the possible challenge that we are going to face in this risk-bounded motion planning problem. In general, we have two challenges: uncertainty propagation, and next, estimating the probability of success or probability of failure. Let's first look at uncertainty propagation. Let's see what I mean by this. Here we are given a nonlinear model of a plane and also nominal trajectories and control inputs. In absence of the uncertainty, if we apply this nominal controllers, plane will follow the given trajectory to the goal point. Now, in presence of uncertainties, like wind disturbances, plane is going to deviate from the given nominal trajectory. If we repeat this process over and over again, each time we are going to see different trajectories for plane. A family of trajectories that represent the location of the plane in the environment. If we look at these trajectories at different time steps, we are going to see such patterns at each sampling time k. These patterns are different realization of uncertain states or different realization of random variables. We can use numerical techniques to find the probability distributions that describes and explains these sample points in the environment. So this shows that since we have probabilistic uncertainties in the dynamics, the states of the dynamics are also probabilistic and have some probability distribution. And to be able to address risk-bounded planning, we need to model and represent this probability distribution. But in general, this is a challenging problem, so we don't have any analytical solution to find these probability distributions for a given any arbitrary models of the robot. So the first challenge is uncertainty propagation. How we describe and model this probability distribution of the state at each sampling time k. Next challenge is estimating the probability of collision. So from the definition of the risk, we need to find this probability that the state at time k collides with the obstacle. And from the definition of probability, we need to deal with this integrals. Here we have multivariate integral with respect to probability distribution of states defined over the region of obstacles. Again, in general, we don't have any analytical solution to calculate this integral. So to be able to evaluate our chance constraints, so we have to calculate this integral so that we can verify the risk. One possible technique is to use sampling-based approaches like Monte Carlo to approximate the integral and estimate the risk. But the question is, given the estimates of risk, how do you want to verify this chance constraint? based on this chance constraint, the true value of the risk should be less than delta. But here we only have the estimates. So how we can verify this chance constraint given the estimates of the risk?
What's the question?
So we are given the estimates of the risk. Now, based on these estimates, we want to verify this chance constraint. So based on this chance, the true value of the risk should be bounded by delta. But we only have access to the estimates of the risk. So the question is, how should we evaluate? So in general, to satisfy this constraint, the upper bound of the risk should be delta. So if we want to approximate this integral and approximate the risk, we should make sure that this estimates of the risk is the upper bound of the true risk, so that we can satisfy the chance constraint as here. Asking the upper bound to be less than delta will satisfy this chance constraint based on the risk. But in Monte Carlo techniques, we only receive the estimates of the risk, and we have no idea if this estimation is the upper bound or lower bound through the risk. So in general, we cannot guarantee risk constraints when we are using Monte Carlo-based techniques. So we have to be careful. We have to look for estimates that satisfy this constraint. The estimation should be upper bound of the true risk. So in general, so we have, I said so, two challenges: uncertain propagation to represent the distribution of states, and finding the estimation of the probability of failure or probability of success. So as a summary, respondent motion planning. So we are in this problem, we are looking for a sequence of the control to shape these probability distributions of the states of the robot to achieve our goals and to satisfy the probabilistic safety constraints. So in this presentation, I'm going to focus on respondent techniques for nonlinear system. Ono this morning talked about respondent techniques for linear system. To be able to show the connection of my techniques to the linear problems, I'm going to briefly review the respondent techniques for Gaussian linear system. So in this problem, so we are given a linear dynamics with additive Gaussian uncertainty. Also, the initial distributions are Gaussian. We are also given a linear safety constraint, linear description of the obstacles or linear description of the safe region. And we are interested in this responded problem. We are looking for the controllers to minimize the cost function with respect to this probabilistic safety constraint. At each time k, probability of collision with the obstacle or probability of remaining in the safe region should be greater than 1 minus delta k. Now, if we look at this linear system, this Gaussian linear system, at each time k, the states of the system is going to have a normal distribution. We have a linear dynamics with initial Gaussian distribution with a Gaussian additive noise. So if we do the uncertainty propagation and look at the distributions of the states at each time k, we are going to see a normal distribution. Why is this true? Why we always observe the normal distribution? Any?
I mean, linear transformation of a Gaussian stays remains a Gaussian.
Right, exactly. So sum of two normal random variable results in another normal random variable, and this is exactly what this linear system is doing. At each time, it is summing a bunch of normal random variables and generating another random variable at the next sampling time. So in the uncertainty propagation step, we just need to model the probability distribution with the Gaussian, and we need to only describe their mean and covariance. At each time k, we can write the mean and the covariance of our uncertainties based on the parameters of the dynamical system as here. So these two equations describe the evolution of the mean and the covariance of the probability distribution of the states along the trajectory. Now, in the next step, since we have a linear safety constraints, we can replace chance constraint, probabilistic safety constraint, in terms of deterministic linear constraint, in terms of mean and the covariance of the probability distributions of states. So as a result, we can transform probabilistic optimization into a deterministic optimization. Here we have a linear constraint, and these new constraints, based on mean and covariance, is going to add some safety margin around the obstacles. This safety margin, the size of the safety margin depends on the covariance of the distribution of the states. So to satisfy this chance constraint at time k, the mean of the probability distribution of the state should remain outside of this safety margin. So this is how we assure safety. So the key point in here is to, okay, let's describe the probability distribution based on the normal distribution and represent them with mean and covariance, and then replace the chance constraint with new deterministic constraint in terms of mean and the covariance of the states. This formulation is based on optimization techniques. We can use the key results in different formats. For example, we can come up with risk-bounded RRT star. So in RRT star, we are looking for a growth tree. So when we are building this tree, at each node, we need to propagate the uncertainties and construct the Gaussian distribution for each node, and then calculate the risk by just looking at the deterministic linear constraint in terms of the mean and the covariance of distribution. And this is how we can find the risk of each node. And by looking at this risk, we can construct risk-bounded paths inside this tree to the goal. Or another format is risk-bounded PRM. So we can construct a graph in the environment. Then we can propagate the uncertainties, which are normal distributions, along each edge. And then we can assign the risk probability of collision for each edge. And then we can call any graph search techniques to construct the risk-bounded paths. For more information about techniques, you can look at the firm paper. Or even we can construct the risk-bounded motion primitives. In offline mode, we can design the different maneuvers for vehicle, and then in the real time, we can propagate our uncertainties, which are the families of the normal distribution along each maneuver. And we can calculate the risk by looking at the linear constraint in terms of the mean and the covariance of the distribution, and then pick the right maneuvers that satisfy our risk-bounded constraints. So in all of these techniques, the key point is the normal distribution representation of uncertainties of states, and replacing the probabilistic constraints with linear deterministic constraint in terms of mean and covariance. Now let's look at risk-bounded techniques for nonlinear planning. So in general, in risk-bounded nonlinear planning, we need to deal with nonlinear constraints. This nonlinear constraint could come from the nonlinear dynamics of the system or nonlinear safety constraints. For example, nonlinear and non-convex representation of the obstacles in the environment. Now, in such setup, instead of representing the distribution by only mean and covariance, I'm going to represent the distribution by higher order statistics called moments. So moment of order d of a random variable is defined as expected value of x to the d. So we will see that moment of order 1 and 2 are nothing but the mean and the covariance of the distribution. So here, instead of using mean and covariance, I need to use higher order statistics because we are not going to see a normal distribution because of the nonlinearities. So to be able to represent arbitrary distributions, I'm going to use a vector of moments. And then, instead of replacing the probabilistic constraints in terms of linear constraint, in terms of mean and the covariance, I'm going to replace the nonlinear probabilistic constraints in terms of linear metrics inequality in terms of the moments. Linear inequalities versus linear metrics inequality. These constraints are also convex, and we can efficiently solve them using convex solvers. So this is the main overview of the techniques. We are going to represent a distribution by set of moments and then replace the probabilistic constraints with linear metric inequality.
What's the difference between linear and matrix?
Yeah, what's that? Yeah, we will see. So, to be able to address the respondent nonlinear plannings, I'm going to define two general frameworks. One is chance optimization, and the second one is chance constraint optimization. In chance optimization, we are looking for design parameters to maximize the probability of success. So what is success? It comes from the nature of problem. So I only assume that success is a nonlinear function of design parameters and uncertain parameters. Like this success could be reaching to the goal region or avoiding obstacles, or even it could be maximizing a profit in a trade. So these formulations are general, and we can reformulate many different problems in different domains as a particular case of these probabilistic optimization. For example, in the first example, so we have a for asset with uncertain rate of Q, and X's are the invested money. So the success is defined as achieving a return higher than predefined value R star. So this would be our return. Then here the success is defined as, so here what we are seeing is a polynomial inequality in terms of the uncertain parameters, Q, which is our uncertain rate, and also design parameters, which are our invested money. So the success is to having this return to be greater than predefined value R star. So then in general, we can represent the success set in terms of polynomial inequalities. A polynomial based on design parameters and uncertain parameters. Exactly what we are seeing, a polynomial in terms of uncertain parameters Q and design parameters X. Now look at the second example here. So we have obstacle avoidance problem. So and success is defined as remaining in the safe region in the next time step. From the nonlinear dynamics, we can define success in terms of design parameters, which are control inputs, and uncertain parameters, which are omega. So, and if we have a polynomial description of the dynamical systems and the safe sets, we can represent the success set in terms of a polynomial described in design parameters and uncertain parameters. So in general, the success is a nonlinear or polynomial function of design parameter and uncertain. Now, so as I said, in chance optimization, we are looking for design parameters to maximize the probability of success. But in chance constraint optimization, instead of maximizing the probability of success, we just want to make sure that probability of success is greater than predefined value 1 minus delta, or equivalently, probability of failure is less than predefined value delta. So in this talk, I'm going to show that how we can solve this probabilistic optimization efficiently. And then, as I said, we can reformulate different problems from different domains as a particular case of these optimization problems. So in this talk, I'm going to look at 3 problems from the control and robotics domain. So in the first problem, we are going to address risk-bounded trajectory planning in uncertain environments. In this problem, we have probabilistic obstacles. So, for example, the location, size, and geometry of obstacles are uncertain, and we want to find a risk-bounded trajectory to get to the goal point from the initial point. For this, we are going to construct a new map that we call a risk contours map. This map represents the risk of different points in the region, so we can use this map to construct our trajectory to the goal. The next problem, we are going to look at nonlinear controller design for probabilistic nonlinear system using the concept of flow tube. So the goal here is to find nonlinear controllers to follow the given trajectory and make sure that robot stays in the neighborhood of the trajectory despite all uncertainties. We call this neighborhood as a flow tube. So this is how we are going to ensure safety, and we can see this kind of reasoning in SpaceX line systems. In the last problem, we are going to look at reachability analysis of probabilistic nonlinear system with application in autonomous system and Mars soft landing problems. So let's first see how we can solve this problem efficiently. First, so to solve these problems, I'm going to leverage these tools: convex optimization, moment theory, and polynomials. In the first tools, which is about convex optimization, in general, chance optimization and chance constraint optimization are non-convex problems. And in non-convex problems, since we have multiple minima, we cannot guarantee the global optimality. So that's why we like to solve convex optimization problems, because we only have one minima, so we can guarantee the global optimality. We have different class of convex optimization, like linear program. In linear program, we have a linear cost function and linear constraints. And this is one example for the linear program. Another set of convex optimizations are called semi-definite programs. In semi-definite programs, similar to the linear programs, we have a linear cost function and linear constraint, plus an additional constraint, which is called linear matrix inequality. So this matrix should be positive semi-definite. For example, look at this example. We want to find this matrix with unknown entries to minimize the linear cost function with respect to linear constraint in terms of the entries of this matrix, considering this linear matrix inequality that is asking for a positive semi-definite matrix. This constraint is also convex, so we can solve these problems using convex solvers. I am also going to use duality techniques for optimizations. For example, given a linear program, we can define a new linear program that we call it a dual optimization. We can construct this dual optimization using the parameters of the original linear optimization. For example, the parameters of the linear optimization are vector C, B, and matrix A. I can use these parameters to define a new linear optimization, but this time in terms of the new variable y. In the original optimization, we are looking for a vector x. In the dual, we are looking for a vector y. I can do the same with semi-definite programs. Given a semi-definite program, I can find a dual semi-definite program using the parameters of the original SDP. And in general, we can show that, okay, the cost function of the dual, the optimal cost function of the dual is the lower bound of the true cost function. Under some mild condition, we can show that the optimal cost function of the dual and the original problem are same, and there is no duality gap. So why do we care about dual problems? We can simply go and solve the original convex problems. Why do we need to look at the dual optimization problems? Any?
It's easier.
Yes, that could be the case. Sometimes we have better solvers for dual optimization. But in general, since dual optimizations are based on a new set of variables, this new set of variables gives a new insight into the original problems. We get a new perspective about the original problem, so we can solve the problem more efficiently by looking at the dual problems. So what I'm going to do in this talk, I'm going to reformulate the chance optimization with semi-definite programs, and then I'm going to look at the dual of that semi-definite programs to solve the chance constraint optimization. So the next tool is the moment. So given a probability distribution, we can use a probability distribution of a random variable x, and instead we can use this integral to calculate the probability of collision. In this talk, I'm going to use two concepts for probability distribution. One concept is the support set of distribution. Support set is nothing but our uncertainty set, a set that our distribution is defined upon that set. For example, here we are given a uniform probability distribution defined over the interval A and B. The support of distribution is that interval A and B. Or in the case that we are given a delta distribution is defined over one point x star. So the support of this probability distribution would be that point. I'm going to use this delta distribution when I'm solving chance optimization problem. So given a point, a deterministic point x star, we can always assign a delta distribution to that point. So given a delta distribution, we can always extract the point by looking at its support. One point and a delta distribution defined on top of it. The next concept is the moment. Moment of order alpha of a random variable x is defined as expected value of x to the alpha. So for example, the first moment is expected value of the x, and this is nothing but mean. And second moment is described as here, power of 2. And from the definition of the covariance, we can describe covariance in terms of the first and the second moments. So mean and covariance are nothing but first and the second moments. And also another important moment is the zero order moment, which is the expected value of this term. And this is called volume of the distribution. Now, throughout this lecture, I'm going to use the moment, sequence of the moment, to represent the probability distribution. We saw that in the linear case, we use normal distribution and represents the distribution with mean and covariance are nothing but the first and second moment. But in here, since we are going to have arbitrary distribution, I'm going to use not only the first two moments, but also higher order moments up to some finite order d. So the last tool would be a polynomial. So in general, polynomial functions are linear sum of powers of x or monomials. So here we are seeing a one-dimensional polynomial in terms of variable x1, and here we are seeing two-dimensional polynomials in terms of x1 and x2. Polynomials in general are important because we can approximate any arbitrary continuous function in terms of polynomials. In this talk, I'm going to use polynomials to represent my sets. Safe set, unsafe set, or sets that describe the success. For example, here we are seeing a circle-shaped obstacle described by the level steps of this polynomial. And here we have an uncertain obstacles. We have a circle-shaped obstacle with uncertain radius omega, as described here. The omega is uncertain, so here we are seeing a probabilistic uncertainty in the size of obstacles. This omega could change based on some distribution. And in general, we can represent any non-convex and complex set by the level sets of the polynomials, as here. Now, so as I said, I'm going to use moment techniques and polynomials to find a semi-definite linear matrix inequality representation of the original chance optimization. So since this is convex, I can solve it efficiently. And then in the next step, I'm going to look at the dual problems and solve the chance constraint optimization. Let's look at the chance optimization. So as I said in chance optimization, we are looking for the design parameters to maximize the probability of success. So in this problem, we have two set of parameters. Design parameters x and uncertain parameters q with known probability distribution mu q. And this is and this polynomial p describes our success set. So we are trying to maximize the probability of success. So the main idea is to, instead of looking for design parameters x, I'm going to look for its probability distribution. And what do I mean by this? So I'm going to treat x, the design parameters, as a random variable. I'm going to assign an unknown probability distribution to my design parameters. This is unknown. And then once we do that, we are going to get a parameters of x with unknown probability distribution, a set of parameters with known probability distribution. So I'm going to reformulate the chance optimization in terms of these distributions. The unknown distribution of the x and known distribution of the uncertainties. And so as a result, I'm going to reformulate the original chance optimization in the probability domain space in terms of the mu x and mu q. And this will gives me an infinite dimensional linear program, a convex optimization. Then once we solve this, we can actually extract so from the obtained distribution, we are going to extract the true solution of the original problem. In the next step, instead of looking for probability distribution, I'm going to look for a moment sequence of the probability distribution. I'm going to reformulate everything in terms of the moments of probability distribution mu x, moments of probability distribution mu q, and this is going to give us a finite semi-definite programs, a finite convex optimization that we can solve it efficiently to find the solution of original chance optimization. So first, let's look at the step one. So once we assign the unknown probability distribution, from the definition of the probability and the integrals that appears inside the definition of probability, we can find a new optimization in terms of the distribution as here. So in this problem, we are looking for an unknown probability distribution of the design parameters mu x, and also a slack distribution to maximize this linear constraint with respect to linear constraints. The support of the measure mu x should be in the space of my design parameters, and the support of the distribution mu should be in the set that describes my success. This is a linear program, and we can show that by these two problems are equivalent. The original problem of chance optimization, the new problem that is described based on the probability distribution. These two problems are equivalent, and if x star is a solution of the original chance optimization problem, the optimal solution of the problem in the distribution space is going to be a delta distribution defined over the solution of the chance optimization. So by solving this problem, we can get delta and look at its support and construct the true solution of the original problem. So although here we have a linear program in terms of distribution, the size of these distributions are infinite. So to be able to solve this optimization, in the next step, I'm going to reformulate the cost and constraints of this optimization in terms of the moments. In terms of the moments of distributions mu x, mu, and mu q. For this, I'm going to use a standard results on relation of distribution and moments. So based on these results, moments of distribution supported on this set defined by polynomials should satisfy this linear matrix inequality in terms of moments. What we are seeing here, so it's a moment matrix of order D constructed by the information of the moments up to order D. This is the one example for the moment matrix. And the second one is localizing matrix constructed by the moment information of the distribution and the polynomial that describes the support set. This is one example of the localizing matrix. So using this linear matrix inequality, we can translate the problem in the distribution space into the moment space. Instead of looking for distribution, I'm looking for the moments, and I'm using the relationship between the moments and the distribution to translate these constraints. So here we have linear matrix inequality based on the moments of the distributions.
But so this greater than or equal to 0 here means in terms of the semi-definite matrix.
Yeah.
But on the left, what is it? We're going to this.
So this part?
Yeah.
So this means that this probability distribution should be bounded by this
So it's just
graph.
everywhere.
Yeah.
Okay.
So we can show that by solving this finite semi-definite program, as I increase the size of matrices, or as I use the high order information of the moments, we are going to get the moments sequence of the optimal probability distribution. That's a solution of our problems defined in the distribution space. So instead of solving chance optimization, I'm going to construct the semi-definite program moments and get the moments, and from that moment represents this distribution, which in its support is our true solution. And to solve chance optimization, you don't need to go through all these details and steps. So I use Globtopoly, which is a MATLAB package for moment-based semi-definite program. You can download the sample codes from my GitHub. So you just only need to give the polynomial that describes success set and also the moments of the distribution. Then it automatically generates the moment space STP. It calls convex solvers like Mosaic or Sedumi, and it solves and generates the solution of the original chance constraint optimization. Okay, so now let's look at chance constraint optimization. So in chance constraint optimization, I'm looking for design parameters to make sure that probability of success is greater than 1 minus delta. Here I'm going to do something more. Instead of looking for one design parameters, I'm going to look for all design parameters that satisfies this probabilistic constraint. This is called chance constraint set. For any point inside this set, the probability of success is guaranteed to be greater than 1 minus delta. And this is called chance constraint because we define this set in terms of probabilistic constraints. So to construct these chance constraints, I'm going to use a polynomial approximation of this probabilistic constraint. I'm going to replace this probabilistic constraint with a deterministic constraint in terms of the polynomial denoted by p-R term. So this set, this level set of the polynomial describes my chance constraint. Any point inside this set, for any point inside this set, the probability of success is guaranteed to be 1 minus delta. And to find this p-R term, I'm going to look at the dual problem. So this is our finite semi-definite program constructed in the moment space. By applying the standard duality results of semi-definite programs, I'm going to get a dual semi-definite program, this time in terms of the polynomials. Then the output of this dual semi-definite program is a polynomial that I call a p-R term. Then we can show that for any given design parameter x star, this p-R term represents a upper bound approximation of the probability of success for that design problem. So as a result, I can use this polynomial level set with respect to the p-R term to come up with the outer approximation of my chance constraint set. So by looking at the dual problem of the STPs and also looking at the polynomial description of the success set, I can come up with the outer approximation of the chance constraint set. And we can also find the inner approximations by looking at the complement set, which is the failure set. So as a result, by solving the dual semi-definite programs, we are going to get two polynomials, p-outer and p-inner, and such that the level sets of these polynomials describe our chance constraint set. And this is nothing but polynomial approximation of the chance constraint. I'm replacing the probabilistic constraint in terms of deterministic polynomials. So let's wrap up this section. So as a summary of what I did, solve chance optimization. So the goal was to reformulate the nonlinear chance optimization as a semi-definite program. And to obtain the semi-definite program, what I did, instead of looking for design parameters, I assigned the unknown probability distribution to my design parameters. And I reformulated the original chance optimization in terms of the probability distribution. And then to be able to solve this new problem, instead of looking for the distribution, we looked at the moments of the distribution by applying the standard results of the moment theory. And this gives us this finite semi-definite program that we can call efficient solvers or packages like Globtopoly to solve this STP and find a solution of the chance optimization problem. And for the chance constraint optimization, what we did, so we looked at the dual STP of the chance optimization. Once we obtained the STP for chance optimization, we applied the standard results of the duality of STPs. We find the dual problems. The output of that dual STP is going to be a polynomial P outer and P inner. And then we describe the inner and outer approximation of the chance constraints as here. Now let's see how we can use these results in control and responder planning. So first application is responder trajectory planning in uncertain environments. So in this problem, we have probabilistic uncertainties that comes from the obstacles. So we have uncertain probabilistic uncertainties in location, size, and geometry of the obstacles in the environment. And the goal is to find the responder trajectory to control the robot. Now in this setup, instead of working with ordinary map that only shows free and obstacle regions, the goal is to construct a new map that represents the risk information of different regions in the environment. And we call this risk counters map. So to construct such map, I'm going to define the notion of this delta risk counters, which is a set of all points in the environment whose risk, whose probability of collision with these uncertain obstacles is less or equal to delta. Then I'm going to construct risk counters as a collection of these delta risk counters with different risk levels delta. For example, here we are seeing different delta risk levels with associated risk. The outside of each counter, the risk of failure is less than associated value delta. For example, outside of this first counter, the risk is less than 90%. And inside the set, the risk of collision is greater than 90%. Now, we can use this risk counters map for respondent motion planning. In respondent motion planning, we are looking for a trajectory PT to drive the robot from initial state to the goal state, considering probabilistic safety constraint. Probability of collision over trajectory with each obstacle at each time phase should be bounded by predefined value delta over acceptable risk levels. Now, we can replace this probabilistic constraint with deterministic constraint in terms of the delta risk counters of the obstacles. And as a result, since we have a deterministic constraints, we can call any motion planning algorithm like RRT star or PRM to construct our trajectory. We only need to make sure that obtained trajectory is always inside the delta risk counters of the obstacles. For example, here we are seeing the delta risk counters of each obstacle. Outside these counters, the risk of collision with these obstacles is less than delta. Now, to construct these delta risk counters, so from the definition of the delta risk counters, which is the set of all points whose risk is less than or equal delta, we need to deal with this probabilistic constraint. The probability of collision should be less than delta. And this is nothing but our chance constraint that we already saw this. So the design parameters are the points in the environment, and the success set is the remaining the safe region. So as I described, we can replace the chance constraints in terms of polynomials by looking at the dual STPs. So we are going to get a polynomial P inner by looking at its sublevel sets, delta sublevel sets, a region that this polynomial is less than delta, which is this region. This region is going to describe the inner approximation of the delta risk counters. In any point in that region, the risk of collision with uncertain obstacles is less than delta. And also for the outer approximation, we are going to get a polynomial P outer by looking at the super 1 minus delta level sets. The region that is polynomial is greater than 1 minus delta. This region is going to represent an outer approximation of the delta risk counters.
Is the the number of moments that you have, is it related to the degree of the polynomial that you'll get?
Yeah, exactly.
Yeah, it's the same.
Yeah. So in the original STP, where we are looking for moments of order D, when we are finding the dual STPs, we are going to look for polynomials of order D. That's how they are related. Now let's look at a simple example. In here, we have a uncertain circle-shaped obstacle. Its radius omega is uncertain. It has a uniform distribution. Then by solving the dual STPs, I'm going to get this polynomial. Each different 1 minus delta level sets. The region that this polynomial is less than 1 minus delta for different values of the delta is going to represent the outer approximation of the delta risk counters. So outside each counter line, the risk is less than assigned value. And similarly, we can find the inner approximation by looking at the delta sublevels of these polynomials. As another example, so here, so we have an uncertain obstacle described by this polynomial with random parameter omega. So we can see a different shape of obstacles for different values of the uncertainty. Omega uncertain parameters is a random between 0 and 1 with the probability distribution of beta. So for omega 0, we are going to see that the smaller obstacle. For omega 1, we are going to observe that bigger one. The goal is to drive the robot from the start point to the goal point. And this trajectory is a robust trajectory, robust plan for the robot. Why this is a robust trajectory? What's that?
There's noise.
No. So this is robust because for all values of the uncertainty is always safe. So
Robust means that there's no absolutely zero risk.
in robust means that instead of working with the probability distribution, we should look at the uncertainty set. So here our uncertainty set is an interval between 0 and 1. So for all values of the omega, this trajectory should be obstacle-free. Now, so by solving the dual STPs, I find this polynomial, I look at its delta counter sets, and this is the delta risk counters for the associated risk 1%. Inside this region, probability of collision with this uncertain obstacles is less than 1%. So I can use this space to construct a less conservative path to the goal, from initial point to the goal state. So by considering risk and probabilities, we can come up with less conservative solutions and trajectories. And the last example, so we have an uncertain probabilistic pattern for a crowd. So this group of people is described by the location of this crowd, described by this polynomial inequality. Omega is our uncertain parameters. Omega is a beta distribution between 0 and 1. For different values of this uncertainty, we are going to set different patterns of people. Here we have a connected shape up to disconnected regions. So this is the random location of a group of people or swarm. So by constructing the delta risk counters, by solving the dual STPs, by looking at the delta level set, this is going to be a set for which the risk of collision with this pattern is greater than 50%. Or equivalently, this is the pattern that I'm going to see with the probability of greater than 50% for my random pattern. And similarly, this is a set that probability of collision is greater than 95%, or equivalently, this is a pattern that we are going to observe with the probability of greater than 95% for that random group. So for more information, so yeah, you can look at our recent RSS paper on this topic. The next problem is designing nonlinear controllers for probabilistic nonlinear systems. So in this problem, so as we saw, in presence of uncertainties, the trajectory of robot is going to deviate from the design trajectory. So the goal here is, okay, so while we're tracking the nominal trajectory, we want to make sure that the trajectory of the robot always remains in the neighborhood of the planned trajectory. And we call this neighborhood a flow tube. So by doing so, for safety, we only need to make sure that the flow tube is obstacle-free. Although the robot, the drone, is going to deviate from the planned trajectory, since we know that it's always going to remain inside the flow tube, so for safety, we only need to make sure that this flow tube is obstacle-free. We can also see a similar reasoning in the SpaceX systems. So we can design trajectories and associated funnels for different steps of the mission. And then we need to design a controller to make sure that the system follows the nominal trajectories and always remains inside this flow tube despite all uncertainties and disturbances. Now I'm going to formulate this problem as a chance optimization. So in this problem, so we are given a continuous nonlinear space model, and also we are given a nominal trajectories, x star and u star. In the absence of uncertainties, if we apply nominal input u star, the robot is going to follow this nominal trajectory. This happens when we have no uncertainties. Then I define the flow tube, as I said, a neighborhood around the nominal trajectory of the star. I describe these flow tubes at each time k with polynomials. For example, it could be a circle-shaped flow tubes. For example, at each time k, we are going to see a circle with the radius of epsilon that describes my neighborhood and my flow tube at time k. So what is the goal? Designing time-varying nonlinear feedback controller, UK, such that the trajectory of the robot follows the given nominal trajectory and always remains inside these defined flow tubes. So I assume that my controller has a polynomial structure. So U star is a given nominal controller, and I assume that the U bar is a polynomial state feedback in terms of the error signal. So when we want to design, so we are going to look at the coefficients of this polynomial feedback. So this is what I mean by designing. We are going to look at the coefficient polynomials that describe our nonlinear state feedback controllers. So we can reformulate this problem as a chance optimization problem. What is success? States should follow the given trajectory and remain inside the flow tubes. What are the design parameters? The parameters of the controllers for all time steps. And then use the approach that I just described. Construct the semi-definite programs and solve the problems. But the problem in this problem, I'm going to look for all the parameters of the controllers for all time steps. For long planning horizons, we are going to get a large chance optimization, and as a result, a large semi-definite program. And that semi-definite program can easily get intractable. So to avoid this, I'm going to use sequential chance optimization. So what I'm doing, I'm breaking the original chance optimization into a set of smaller chance optimization. So in this formulation, at each time k, I solve one smaller chance optimization to only find the parameters of the U at that particular time k. Instead of looking for all controllers, I'm looking only for the controllers at that time k. And what is success? I want to find this UK such that the states at the next sampling time belongs to our designed flow tubes. For example, consider this example. So here we are at time k0. we are given the initial distribution of the states. This is our nominal trajectory. This is our flow tube at time k1. So we are looking for the controller at time 0 to maximize this probability that the states at time 1 belongs to the flow tube. So one smaller chance optimization problem. Now we can repeat this process in the next step. Next step, we are going to look for controller at time 1 such that the probability of states belonging to the flow tube in the next sampling time step becomes maximum. But in here, so to be able to solve this chance optimization, I need the information of the distribution of the states. In the first step, the initial distributions are given. But in here, we have to calculate, or we have to propagate the uncertainties. So what I need is a moment description of this distribution. From the definition of the moments and dynamics, I can describe the moments at time 1 based on the moments of the distribution at time 0 and the controller that we just designed. So by doing the uncertainty propagation, we are going to find the moments of distribution of the state at time 1, and then we are going to look for a controller that maximizes this probability. So we can, by repeating this process, we can design the nonlinear controllers along the trajectories. We can actually do this in the offline time. In offline time, we can design different maneuvers, for example, for a vehicle, and then design these tube-based controllers. And then by designing these controllers in offline, in the real time, to assure safety, I just need to make sure that these tubes are obstacle-free. So design everything in offline and use the result in real time for safety. The last example is about reachability set of probabilistic nonlinear system. This is how we define reachability set for deterministic systems. In deterministic systems, we have a deterministic nonlinear dynamics. We are also given input constraints. At each time k, inputs should belong to a set that represents our control constraints, and also we are given a target set, xt. Now, given these parameters, we are looking for a set of initial states, x0, for which that target set is reachable in t steps under the input constraints. For example, consider this vehicle scenario. So we have the dynamics of the vehicle. We are given this target set. Also, we have this constraints. So this initial set, which is called backward reachable set, for any point inside this set, there is a controller that satisfies our constraint and drives this vehicle into this set in t time steps. Note that we are not, so in here, so I only care about this set itself. We are not looking for the controllers. We just find a set of initial conditions for which we are guaranteed to get to the goal, considering the temporal constraint, t, and input constraints. So how we can use this backward reachability set to assure safety? So let's assume this target set is an obstacle set that we need to avoid. So to remain safe, we have to remain outside of this set x0, because based on the definition, if we remain outside, there is no controllers to go and hit the obstacles. So that problem becomes infeasible. Or similarly, if this is a destination, to be able to get to this destination, considering the temporal constraints and input constraints, we should always start from this set to get to the points. Because this kind of reasoning is in Mars soft landing problem. So in that problem, we are looking for an initial set so that we can land on the target set, given the temporal constraint and the fuel constraints. So this initial set is a backward reachability set of the landing site of the spaceship. Now, this was a differential reachability set for deterministic system. Now I'm going to come up with its probabilistic version. So I define chance constraint backward reachability sets. So in this problem, we are given nonlinear probabilistic dynamics with uncertain parameters omega with some probability distribution. We are given target set. The target set itself also has some uncertainties. For example, the location of the obstacles is uncertain. And we are also having the constraint for the controllers. Then I define the chance constraint backward reachability set as here. So we want to find a set of initial states for which the probability of, if we start from this set, the probability of achieving the goal is greater than 1 minus delta. So any points, any initial points for the vehicle, if we start from this point with the probability of 1 minus delta, with the probability greater than 1 minus delta, we are going to get to this target set considering the temporal and input constraints. So we can reformulate this problem as a chance constraint optimization, where so in the chance constraint optimization, the success is defined as reaching the target in t steps, considering the input constraints, and the design parameters is all initial conditions for our dynamics. So this results in this chance constraint, and again we can use semi-definite program results to come up with a polynomial approximation of this set and get to construct the inner and outer approximation of the reachable sets for safety. Okay, so let's wrap up. So in this presentation, so I show that so we need to look at responded techniques to deal with probabilistic uncertainties and also get less conservative solutions. So what we did in the case of linear responded techniques, so we modeled the distributions in terms of the normal distributions and the mean and covariance, and we replaced the chance constraint with deterministic linear constraint in terms of mean and the covariance. And for the nonlinear case, so we reformulated the nonlinear chance optimization chance constraints as semi-definite programs in terms of the moment, and we call the efficient convex solvers to solve the obtain STPs. And I show that so we can reformulate many different problems as a particular case of chance or chance constraint optimization. There are many other details. So for this, so please look at our literature. So the main results are in our SciM journal optimization paper, and the applications are in RSS and CDC papers. Different application of chance and chance constraint optimization. Also, I'm going to actually teach a course on this topic at MIT this fall. So if you check my website, I'm going to put the lecture notes and probability codes that provides more details for different techniques to deal with uncertainties and response techniques. Okay, thank you.
So we have some time for questions. Any questions?
Yeah, I guess one thing I don't really understand is if you propagate according to dynamics, let's say you start with a Gaussian, I mean, whatever distribution you have, it'll just disperse, right?
For the linear dynamics or
Non-linear.
okay. But even if the initial distribution is Gaussian,
I'm just saying that, like, whatever distribution you start with, like, it should just disperse until the point where, why does it keep concentrating? That's what, like, you don't have perception of anything visually.
so where? So in general, we are going to, yeah, so actually expanding funnels. Yeah, that's true. Unless we use some kind of observation to actually shrink down something. Yeah, that's right.
But here you weren't using it.
No, I didn't talk about any.
So you can't have really long planning horizon.
Yeah. So it depends on the levels of the uncertainty. So if you have the smaller, we can. So there are a set of techniques called covariance control. So they show that so for the linear dynamics, under some condition, without observation, actually, you can control covariance. Just shrink the covariance. So I suggest you look at those techniques, covariance control.
No question?
Thanks. I really enjoyed your talk. So I have two questions. Can you talk a little bit about what types of uncertainty? So are you just doing obstacles, like sensor uncertainty on detecting obstacles, or are you taking into account dynamics?
So in general, so in the problem, I have two sources: the uncertainty that comes from the dynamics of the robot itself, and the uncertainty that comes from the description of the safety constraint, for example, probabilistic obstacle.
Okay.
So it
And
could
you're
be.
taking into account both.
What's that?
And you're taking into account both. And you're taking into account both when you're.
Yeah, could be anything. So on the paper, I don't have any restriction. So the problem is, so we should avoid large simulation program, you know.
And the other thing I was going to ask is how big are the problems that you're.
So as you see, so I'm trying to break the original semi-definite program into smaller semi-definite programs. And what I'm doing, I'm also doing offline calculation and use the results in real time. For example, construct the risk contours mapping offline and use the results in real time. It's offline, online, offline, and also reducing the size.
How are you trying to break them into smaller?
So, for example, in the flow tube case, so it depends on the problem. So instead of looking for the all controllers over the planning horizon, I am I'm only looking for controller at each sample, at each time.
So it's shorter, right?
Yeah, shorter.
Okay, great. So let's try to speak again.